Hello and welcome to tutorial 15. Our topic today is an introduction to nuclear chemistry. Before we get started with that, just a quick reminder that the notes to accompany this video tutorial are available online through my website. And with that said, let's go ahead and get started. So in previous tutorials, we have talked about chemical reactions. And we learned that these chemical reactions involve the valence electrons. And the valence electrons can be transferred from one atom to another, forming cations and anions in ionic compounds. These valence electrons can also be shared between atoms in the formation of molecular compounds. Nuclear reactions are completely different. Nuclear reactions involve spontaneous changes within the nucleus of an atom. And these spontaneous changes are accompanied by the release of great amounts of energy. So in order to really understand nuclear reactions, we have to first make sure that we really understand the structure of atoms, specifically their nucleus. And we also need to make sure that we understand the concept of isotopes. So we're going to start out today with a little bit of review. It's actually from tutorial 4 topics. So if you want a greater review, you can go back to tutorial number 4. Otherwise, I'll give a quick review right now, starting with atomic structure. So we already learned that the protons and the neutrons reside in a dense central core called the nucleus. So I'll label this as protons and neutrons. And the electrons reside outside of the nucleus in orbitals. Recall that the number of protons within the nucleus is fundamental to the identity of the element. And we can always find the number of protons by looking at the periodic table atomic number. So let's just pretend that we're looking at carbon in the periodic table. So I'm just going to write the atomic number and the mass number down here. Okay, so remember the atomic number sometimes symbolized as Z, capital Z, will always tell you the number of protons in the nucleus for that particular element. So for carbon, it's 6. Carbon has 6 protons in the nucleus. Okay. So number of protons, it's right over here, can be found from the periodic table. I'll write PD for periodic table. And in parentheses, I'll write Z, the atomic number. The number of neutrons within the nucleus can vary. So I'm going to write up here, number of neutrons can vary. Atoms of the same element that have different numbers of neutrons and therefore different masses are related to one another as isotopes. So for example, carbon has 3 naturally occurring isotopes: carbon 12, carbon 13, and carbon 14. And this atomic mass that's given in the periodic table, remember that that is a weighted average mass for all the naturally occurring isotopes of an element. So for carbon, that is the weighted average for these 3 naturally occurring isotopes of carbon. Now, when we're writing the symbol for these 3 isotopes, we want to make sure we can do that correctly so that we can start writing nuclear reactions. So just a quick review of that. Remember that these element symbols need to have a superscript, which gives you the mass number. Remember that the mass number is the sum of the protons and neutrons for that particular isotope. So I'm going to label this here. This is the mass number, sometimes abbreviated as a capital A, and it is the sum of the protons and the neutrons for that particular isotope. And as a subscript in front of the element symbol, the atomic number should be written. So let me go ahead and write here. This is the atomic number. Remember that that is sometimes symbolized as a capital Z, and remember that that is just the number of protons. You can get that from the periodic table. For carbon, it is always going to be 6. Remember, it's fundamental to the identity of the element. So we can go ahead and write an element symbol for carbon-13 and carbon-14 as well. We know that the atomic number is always going to be 6 for carbon, so we can go ahead and write that in as the subscript that comes before the element symbol. But what's going to change for these 3 different isotopes is the mass number. If we want to indicate carbon-13, we've got to change the mass number here to 13. If we're trying to indicate carbon-14, we want to change the mass number to a 14. So clearly, all of these isotopes of carbon will have 6 protons. Again, fundamental to the identity of the element. What varies is the number of neutrons. Carbon-12 must have 6, because remember that this is the sum of the protons and the neutrons. So you can think of that as 6 for the protons plus n equals 12. You're solving for n must be 6. Over here, n must equal 7. 6 plus 7 will give you 13. And for carbon-14, n must be equal to 8. 6 plus 8 will give you 14. Well, these first 2 isotopes of carbon, carbon-12 and carbon-13, are stable. They do not undergo spontaneous changes within their nucleus. They do not undergo nuclear reactions. So I'm going to label that here. I'm going to write that these 2 are stable. Carbon-14 is radioactive. It will undergo spontaneous change within its nucleus. So I'm going to write here, carbon-14 is radioactive. So we're going to talk a little bit about what makes an isotope stable or unstable, radioactive, next when we move on to slide 2. So let's go ahead and erase here. Within the nucleus, there is a nuclear force that holds together those protons and neutrons in that tight, dense core. And that nuclear force is dependent upon the number of neutrons within the nucleus. For lighter atoms, those with atomic number about 20 and below, it seems to take a ratio of about 1 to 1. 1 neutron for every 1 proton to maintain a stable, non-radioactive nucleus. But as an element gets heavier, with atomic numbers greater than 20, it takes more neutrons to hold those positively charged protons together in that tight proximity of the nucleus. And the ratio approaches a relationship of about 1.5 to 1, 1.5 neutrons to every 1 proton. Beyond atomic number 83, there's no number of neutrons that can maintain a stable nucleus. Beyond atomic number 83, all isotopes are radioactive. So let's write those 3 main points up here on the board. So number 1, we said for the lighter atoms, those with an atomic number less than or equal to 20, it takes a relationship of about 1 neutron to every 1 proton to maintain a stable nucleus. It doesn't have to be exactly 1 to 1. It's going to be somewhere close to 1 to 1. As the atoms get heavier, atomic number greater than 20, it takes more neutrons to maintain a stable nucleus. And that relationship approaches about 1.5 to 1. And beyond atomic number 83, everything is radioactive. So I'll write beyond Z. I'll write Z greater than 83. That makes more sense. Z greater than 83, all isotopes are radioactive. Okay. So we can plot this in what's called the band of stability, sometimes called the belt of stability. So let's go ahead and do that now. We're going to do it over here. And on the x-axis, we're going to have the number of protons, or the atomic number. On the y-axis, we'll have the number of neutrons. And I'm going to go ahead and indicate what's supposed to show a 1-to-1 relationship here. This line is for a 1-to-1 relationship. And then I'll go ahead and also show the 1.5 to 1, a line to represent that 1.5 to 1 relationship as well. And then I'll actually put the band of stability in a different color. I'll put it in blue. So up to atomic number 20, we would expect the band of stability, which represents the stable, non-radioactive isotopes, to have about the same slope as this line here that I've drawn for the 1-to-1 relationship. So I'm going to go ahead and, it's not perfect, okay? Like for carbon, for example, we know that carbon-12 and carbon-13 are non-radioactive. We just learned that. So it's not exactly 1-to-1. So I'm going to just kind of write a thick line, sort of lying along that 1-to-1 relationship. And once we get above atomic number 20, it's going to start deviating from that 1-to-1 relationship. And we're going to see that it takes more neutrons to maintain a stable nucleus, and that approaches that relationship of 1.5 to 1. Now beyond atomic number 83, remember that everything beyond atomic number 83, all the isotopes are radioactive. And so the band of stability would halt at atomic number 83. Nothing beyond atomic number 83 is stable. And this band is supposed to represent the isotopes that are stable, non-radioactive. Up to atomic number 20, that's roughly a 1-to-1 relationship of protons to neutrons. From atomic number 20 to 83, that's a greater number of neutrons approaching a relationship of 1.5 to 1. Okay. So anything outside of this band of stability, we could expect to be radioactive. So any isotope that lies outside of this band, we would expect that to be an unstable nucleus, an unstable relationship of protons to neutrons, and we would expect that to be radioactive. All right, so we're going to go on to slide number 3 and talk about some types of nuclear decay. I'm going to leave this band up here because we're going to use that for slide number 3. So we're going to go ahead and just talk about the 3 most common types of nuclear decay: alpha decay, beta decay, and gamma decay. Starting off with alpha decay. In alpha decay, 2 protons and 2 neutrons are ejected from a nucleus as a helium-4 particle, also known as an alpha particle. So I'm going to write here 2 protons and 2 neutrons ejected as a helium-4 particle, also known as an alpha particle. So how does this affect the atomic number and mass number of the atom undergoing this change? Well, we've lost 2 protons, so the atomic number is going to decrease by 2. So a new element is going to be formed. So I'll write here, Z decreases by 2, lost 2 protons. The mass number, A, is going to decrease by 2 plus 2, by 4. Decreases by 4. So Z is going to tell you the identity of the new element formed, and A is going to tell you what isotope of that element is formed. So let's go ahead and write the alpha decay for uranium-238. Okay. So in order to do this, you must first be able to write a proper symbol for uranium-238, for this particular isotope of uranium. So remember, the 238 is written as a superscript before the element symbol, and then the subscript will be the atomic number. Now, if you don't know the atomic number, that's okay. That is what your periodic table is for. Go to your periodic table, find uranium. Its atomic number is always going to be 92. Uranium-238 undergoes spontaneous change within the nucleus, giving off 2 protons and 2 neutrons in the form of an alpha particle. So one of the products formed, and I always like to write it first, is the helium-4 particle. 2 protons and 2 neutrons. So a 2 here and a 4 here. So what is left? What element remains? What element is formed? For that, you're going to need your periodic table. You lost 2 protons, so the new element formed must have only 90 protons in the nucleus. So we're going to go over to the periodic table and we're going to see what element that is. Atomic number 90 has to be thorium. What isotope of thorium? You get that from the mass number, which has decreased by 4. So it is thorium-234. Okay. All right. So these alpha decay reactions are most common in radioactive isotopes that lie beyond the band of stability. So things with atomic number greater than 83 will frequently undergo alpha decay, losing 2 protons and 2 neutrons and approaching, therefore approaching the band of stability. So I'm going to go ahead and write that in the red here. Radioactive isotopes with Z greater than 83 usually, not always, usually undergo alpha decay in their attempt to become more stable and reach the band of stability. All right, so let's go ahead and go on to beta decay. And I think I'm going to need a little bit of room here, so I'm going to go ahead and erase all this information about alpha decay before we go on to that. In beta decay, a neutron spontaneously turns into a proton and an electron. The electron is ejected from the nucleus as a beta particle. So it's right up here. One neutron decomposes into one proton and one electron, the beta particle. And we're going to write that beta particle as E -1, 0 in our nuclear reactions for beta decay. So let's go ahead and write a nuclear reaction for the beta decay of iodine 131. Again, let's grab our periodic table. We are going to need that here. Okay. So first we have to write a proper symbol for iodine 131, which means we need to know its atomic number. Go to the periodic table and find iodine has the atomic number 53. It's going to undergo a spontaneous change to the nucleus, ejecting that beta particle, which we're going to write as a product, E -1, 0. The other element, the new element that is going to form, that's the hardest part here. We have to figure out what it's going to be. So it's good to know how the atomic number and the mass number are going to be affected here. One neutron decomposes into one proton and an electron. So the atomic number Z increases by 1. Increase in the number of protons. The mass number A undergoes no change. Because remember that the mass number is the sum of the protons and the neutrons. You lost a neutron, but you gained a proton. It balances out. So the mass number is not going to change. The identity of the element is going to change because the atomic number will change. So what element forms? Well, it's going to have an atomic number of 54. Notice how these two numbers add up to the number that's over here on the reactant side. So you can kind of check your work here, make sure you're doing everything right. And the mass number, the isotope, will still be 131. So what element is it? Go to the periodic table and find out what element has an atomic number of 54. It is xenon. So from the beta decay of iodine 131, we get a new element formed, xenon 131. All right, so for beta decay, let's write this in the red pen again. Typically, you're going to see beta decay for atoms, radioactive isotopes that lie above the band of stability. So I'll just put a little X up here. All right, radioactive active isotopes above the band of stability, all right, BOS for band of stability, usually undergo beta decay. Because beta decay will drop the number of neutrons one, but increase the number of protons one, and so will approach that more stable neutron to proton ratio. Will approach the band of stability. Okay, last but not least, let's talk about gamma decay. Let's go ahead and race up here so we have a little more room. Okay, gamma decay is not accompanied by a change in mass number or atomic number. And this is because gamma emission is just a form of high energy electromagnetic radiation. It is massless. Unlike the alpha particles and beta particles that we talked about previously, which do have mass. And gamma radiation typically accompanies other types of radioactive decay, like alpha decay and beta decay. And it's really just a form of energy. It allows the newly formed isotope to give off extra energy. So let's write up here gamma decay, and let's write a form of high energy electromagnetic radiation. I'm just going to write EMR for that. It's a long one to write. Accompanies other types of decay. And let's write, it's a way for the newly formed isotope to get rid of energy. And because it is a high energy electromagnetic radiation, it is massless and it causes no change in atomic number or mass number. A for mass number or Z for atomic number. Okay, so sometimes textbooks will not indicate gamma radiation in a nuclear reaction. Other textbooks will. So I like to go ahead and show it, and we symbolize it as gamma with a 0 for the atomic number and a 0 for the mass number, because it is just a form of high energy electromagnetic radiation. It is not a particle. So let's go ahead and write the nuclear decay, beta decay, of cobalt-60, which also is accompanied by the emission of gamma radiation. So we would write this as cobalt-60. We got to look up the atomic number. Grab your periodic table for that. Okay, cobalt, see right here. So 27 is the atomic number. And we just said that it is beta decay, so a beta particle, make sure you know how to write the beta particle, the E, -1 and the 0. What is the new element formed? Well, it's going to have an atomic number of 28, and the mass number is still going to be 60, because remember, in beta decay, one neutron turns into a proton and an electron, a beta particle. So what is this new element that forms? Go to your periodic table and find out what element has atomic number 28. It is nickel. And because we're told that this is accompanied by the release of gamma radiation, I'm going to go ahead and show that. Gamma 0, 0. Okay. Last thing I want to say, and then we'll go ahead and move on to this and go on to slide number 4. A lot of students in an introductory chemistry class are going to say, wait a minute, cobalt-60, I looked at the periodic table and the atomic mass was 58.9. What's going on here? Don't forget that this is specifying a specific isotope of cobalt. Here in the periodic table, the atomic mass is showing the weighted average for all the naturally occurring isotopes of cobalt. So it doesn't necessarily match up to this number, okay? So don't get confused by that. Don't let that throw you off. This is a weighted average for all the naturally occurring isotopes. It's not going to be the same number as you're given in the problem, which is the mass number for a specific isotope of cobalt. Okay. Let's erase here and go on to slide 4. Okay. The rate of nuclear decay is measured in half-life, sometimes symbolized as T1/2. Let me write measured in half-life, T1/2. And half-life refers to the amount of time that it takes for 1/2 of a radioactive sample to decay. And so the rate of decay always follows this curve. Let's say that we start with a 10.0 gram sample. After 1 half-life, we would expect 5 grams to remain. So we started here at 10. After a second half-life, we would expect half of that, or 2.5 grams to remain. After a third half-life, we would expect half of 2.5, or 1.25 grams to remain. And so the curve will always have this general shape for radioactive decay. Now, it doesn't matter if you're talking about a radioactive isotope that has a half-life in the billions of years, and so each of these half-lives is representing billions of years, or a radioactive isotope that has a half-life that is only a fraction of a second. And so each of these half-lives is representing just a fraction of a second. The curve will always be the same general shape. Nuclear medicine is the branch of medicine that uses radioactive isotopes to either diagnose the function of a specific organ or to treat disease. So we will just touch on each of those topics briefly, starting out with diagnostic imaging. In diagnostic imaging, a radioactive isotope is administered to a patient via either ingestion, injection, or even inhalation. And that radioactive isotope is allowed time to circulate to the target area, the target organ, the organ of interest. And once it's reached that area, it begins undergoing radioactive decay and giving off radiation. That radiation is detected externally and used to image that organ. So let's just write a few points up here. So we'll write radioactive isotope administered it's allowed time to circulate to the target area. Once there, it undergoes radioactive decay. And releases radiation that is detected and used to image the organ. Okay, so since it is detected externally, diagnostic imaging must occur with the release of gamma radiation. Gamma radiation, remember, is a high energy form of electromagnetic radiation. It can penetrate through the tissues and exit the body. The alpha particles and beta particles are actual particles. They have mass. They have a lower penetrating ability. And so they would not be able to penetrate out of the body where they could be detected. So I'll write here, must include gamma radiation, gamma decay or gamma radiation. Oops, if I spell it right. Because that's actually the form of radiation that is being detected. All right, so a good example for diagnostic imaging using a radioactive isotope is the use of iodine-123, a radioactive isotope of iodine. And iodine is circulated to the thyroid gland, where it is utilized to synthesize the different thyroid hormones. And so iodine-123 is a great example of a radioactive isotope that is useful for imaging the thyroid. So I'll write here, used to image the thyroid gland. So your body doesn't care what type of iodine it's utilizing to synthesize those molecules that it needs. It'll use any kind of iodine, whether it's radioactive or not. So it will uptake that extra iodine that is administered, that iodine-123, and circulate it directly to that organ of interest, the thyroid gland. There it will undergo decay known as electron capture, which is a type of nuclear reaction that we didn't actually talk about, but that's okay. You can always look it up if you're interested. And that is accompanied by the emission of gamma radiation. And that is the actual radiation that is detected and utilized for the imaging. All right, so we're gonna go ahead and erase here and go on to radiation therapy, the treatment, the use of radioisotopes in the treatment of disease. Okay, radiation therapy. Radiation therapy is used to treat disease, and it can be either internal or external. So we'll talk about each separately. We'll first talk about internal radiation therapy. I'll just write RT for radiation therapy. In internal radiation therapy, a radioactive isotope is administered to a patient, again via either ingestion, injection, or inhalation, but it can also be via surgical implantation. And that radioactive isotope gives off ionizing radiation that is of a level that is great enough to kill malignant cells in that area. Now in this case, it's not the gamma radiation that is important. It is the use of an alpha or a beta emitter that is important, because the alpha particles and the beta particles, being that they do have mass, that they are particles and not just a form of high energy electromagnetic radiation like those gamma rays, they will release their ionizing radiation to a smaller, localized area within the body. They will not penetrate out of the body. They will release that ionizing radiation to a very small, localized region where that malignancy is. Okay, so I'm going to write here alpha or beta decay used to release large amount of ionizing radiation to the site of the malignancy. Okay, external beam radiation therapy we'll talk about next. It's right here, external radiation therapy. Again, I'll just write RT. In external beam radiation therapy, a beam of gamma radiation is aimed at the site of a malignancy. So it has to be gamma because it's external. It needs to have penetrating ability, which the alpha and the beta just won't have. They are particles. They have a lower penetrating ability. So we'll write up here a beam of gamma radiation is aimed at the site of a malignancy in order to kill the malignant cells. Okay, so that's just a brief overview of nuclear medicine and the use in both diagnostic imaging as well as radiation therapy. And that will conclude our tutorial 15. I hope you will consider tuning into problem set 15, where we will be writing lots of reactions for alpha, beta, and gamma decay nuclear reactions. Thank you.